So the topic is innovative mass customization for building technologies. And the idea is that mass customization relates to the ability to provide high volumes and at a reasonable cost. So mainly the idea is to differ from a mass production possibility that is typical of IEC, so architecture, engineering, and construction, but deals more with customization of different products. So this happens in different sectors, mainly more innovative than construction, like, for example, automotive or innovation in digital innovation, where things go very fast and customized for the user because innovation is very near to the user. In construction, this is like less known, and it's mainly a customization that goes through some products to some tools, so it's a little bit less focused than in other sectors, but it's starting to be very important because the tools allow it and the innovative types of machine allow it. So these advanced construction processes that allow mass customization are mainly driven from two enabling factors. The first one is advanced manufacturing technologies. This is a very big boost in how architectural component and building system can be made because it's mainly due to advancement in digital, in cyber systems, in different types of digital fabrication that allow a direct connection between the architect and the construction machine. Then the second enabling factor, quite important, is computational design. Computational design is a way to make parameters. They make you understand which type of design you're doing. So making numbers that you can work with and understand which type of shape, of geometry, or performances you're doing. So some of the projects I will tell you are mainly made here. This one was made with the students in 2013. It was part of a workshop, and it's a form-finding pavilion that used computational tools to develop an innovative shape and then to directly digital fabricate it here at Politecnico. This is the result. It was here nearby in one of our spaces in Politecnico. The idea is to engage the community also in what we do here and to work with the student in our spaces. And this was the form-finding process. So the idea is to customize the design with a specific shape. That is the first one on the top. So the idea to have this hanging curved shape, form-finding, that is mainly dealing with the space because the different entrances are related to the different classrooms. So where you can enter, you have these different spaces. Then we try to understand the performances. So how was it working with the meshing process of understanding the different efforts on the surface. Then a material analysis. So I think what's important today in a way we can customize our design is that we can embed properties of the materials directly in the design. With the material analysis, we use cardboard, that is a very traditional material. Mainly is the one you use to take pizzas, takeaway pizzas. So it's very rigid in one direction and very soft in the other direction because it has a one-directional geometrical load-bearing structure. So we try to optimize the principal stress analysis together with the students, understanding where the main efforts are going. And then we start with a tessellation process to make the different components, understanding which are the main direction, and so to make an optimization that allows to have flat panels. Flat panels are mainly usually much less expensive than curved panels. In construction in general, we have a ratio of increasing of cost in relation to the different curvatures that is 1, 10, 100. So a flat curve is 1, a curved is 10, a double curved is 100. So it's much more expensive to have special components than to have flat components. So in this case, the exercise was how to make the orientation in order to have flat surfaces and also to have a very lightweight structure. So we made an optimization. These are the machines that are here in Politecnico in Bovisa. And we make some basic components, trying to understand how was the shape, how to bend them, how to connect them together, that is a dry assembly connection, and how much void, how much openness we could work with in the structure. So the idea was to work with more or less a 50% of openness. This means that the structure could be lightweight, but at the same time resistant. So it was an effort to find a balance between the two. This was the final effect, trying to understand how it could work. And then we assemble it in components, so like in mega components, because of course the structure is resistant just in its final shape, so it's not resistant in portions. So we made this different exercise to make big portion of the structure and then to assemble it together. And this was the result. It was also quite important to understand how to fix it to the ground, because of course it's not a ground that you can usually use to fix structures, and it's very important for the resistance of the structure because it's a form finding process. So this was the use, as we were saying at the before, between the use of computational tools and digital fabrication to engage directly in the design with the constraints of materials. This is another workshop, always with the students. This is the idea to work with a much more traditional material. It's rattan and wood. And the idea was to make a structure that could be resistant with the weaving technique. Weaving technique is very old. It's typical of the nesting of different types of objects that are everyday used in many countries. And the weaving technique allows to strengthen the resistance of the material due to the specific pattern. So we made different types of studies on the patterns to understand which one could be the most resistant in single tensor, two crossing tensor, three crossing tensor, making different simulation also with quite complex softwares to understand with the different crossing how it could work. We made some FEM analysis also for the stresses because it's a very particular structure, because the idea of our design was that this mega component should be a shading or could be a structure, an internal component, for example, should be resistant by shape, as in the first example. We worked with rattan, that is a very economical material that is mainly used for external furniture usually because it can stay outside. It absorbs water, so it's also an element that can be bended quite easily due to water. So that's what we try to analyze, going with the microscope and trying to understand exactly what's the vascular system of the structure of this wooden system. And so we tried to understand which was the prominent metasystem vessel with which the water would go. So this allows us to understand, here you can see at the microscope, which was the possible curves we can use in our design. So we sort of embedded the design of the curves with the material we had. So in this case, it's the property of rattan. With this information in mind, so it's a more informed design, we made these different types of slime with Kangaroo. It's a simulation software from Grasshopper that is quite easy, let's say, because you can put different types of loads in your structure. And we tried to understand which was the maximum curvature we could have. So we made a sort of double effort. A first practical one, so to understand bending the structure, what could happen, and the second one that was more digital, so what was the chance and the possibility to bend this structure. And this was the result. So we made some supports in the meantime, because here too, like the first case, the structure is not self-standing before the final configuration. And this was the result always here in Polytechnic in the space, because it was also done with the students. We had some issues with the rattan, because the rattan is a very resistant material. So when we bought this rattan to use it for our project, in some ways it was not bending enough. So we had to use more water to try to bend it. But this means that also the holes, that was really perfect, the tolerances were near 1 millimeter, was not exactly what we expected. So we had to work with the tolerances between the rattan structure and the holes of the structure to make it perfectly. This is another case of, let's say, mass customization that is the topic of today's lecture. This is a pavilion of UIA in Expo 2015. And in this project, we were engaged with the idea of reducing the number of panels for the UIA pavilion and understanding how many types of ripples we can work with the pavilion. This is a project from Foster and Partners, and there was a main contractor, and and also a producer or manufacturers of GRC that is can build. And we were in the middle with the construction company that is called Rimon to work and understand which was the best configuration of panels and to find a solution to reduce the number of panels and find a solution that could be cost-effective and in time. This is the design process from Foster's, so the idea to have drones and understand how sand dunes moves, because they are moving a lot. We always think a desert as a fixed natural system, while it's moving very much during day and night. And so they try to map what are the ripples that happens in the desert due to the wind, and so this was the idea from the designers. Then they tried to make small panels to understand which could be a panelization that could work. This is due for the envelope mainly. And the idea was to have 4 tiling periodic systems, panels that could be continuous. So even if you rotate the different configuration from A to C to D, you would probably have the same junction. So it could seem to be very different even if it was the same. So there was different trials in Foster and Partner Studios, and this was mainly our first work in the project, was to reducing the number of panels and then to understand maybe a way that could be more complicated, so that make big panels, but also most cost-effective and easy transport inside. Expo has a very specific issue that is time, because they have to open on the 1st of May of this year, so you cannot afford to have delays. So this was one of the main issues, was let's try to make a solution that maybe could be a little bit more difficult in the design phase and maybe manufacturing, but that can assure us to be very fast on site. So these were the different type of panels. At the end, the height was at least more or less 12 meters, because the idea is that you can stay in the transportation dimension. Usually 12 meters is the maximum transportation dimension after you have to take care of more issues when you transport materials. And then we divided the panels to be sure that it could have these ripples working together. This was on site, so you can see like the very big panels, the structure, and on the back of the structure they have this steel structure that is completely part of the components. It's a sort of unitized system that you can hang to the wall with a crane. All the project, of course, was done in BIM, not only to understand the clashes, let's say, but also to understand how the different systems work together. HVAC, structure, cladding, timing. It was a very useful system for the management of the project and not only the design. These are the molds, so as you can see the human scale, they were manufacturers in Hong Kong. So it was quite a far manufacturing site, and then they were shipped to Genova and then came in Milan. And this was also another big issue, because it was quite difficult to follow this very big pieces movement during the period they had to come. And some panels disappeared because of the pirates in the Caribbean Sea, and so some of them has to come with the flight in another specific track just for the site. But then at the end, the result was quite successful, because we could make different types of panels. We had molds, so that means that it was quite easy to make these different types of ripples, and the big dimension allowed to be very fast. This is, I think, additive manufacturing is very typical of mass customization, so the idea that you can customize your own design. It's a line of research that is working a lot in also other sectors. Automotive, motors, is mainly metal additive manufacturing. And here when we are making different studies, one of them is with junctions, so to understand the different types of system and materials, how they can work together. I think there's a lot of research, and it's quite important for architects to work with different types of materials. So which are the properties I can really design? Which are the type of performances I can work with, I can customize for my own design with an average cost that is typical of construction. This is what was part of an exhibition we made for 2015, and it's called Digital Takes Command. And here we worked with junction. So what are the junctions in construction? They are very important because mainly it's not only of joining two systems, but it's also what happens with the different types of junction. Are they open? Are they closed? Do I have a frame? So this is very important to design from the very beginning because it will completely affect your design. It's something sometimes with the additive manufacturing we forget, but it's one of the most important because having good joints means that at the end your construction system will face different issues and will probably be different also from an aesthetical point of view. This is always in the direction of customization. I think you will see it now in a couple of weeks, and here in Politecnico in the south area. It's a completely 3D printed load responsive cellular envelope with additive manufacturing, where all the components have been designed for the specific loads of the component. So it mainly comes from a lattice-based cellular solid, so it's interconnected net of struts and pin joined. I think some examples could be, for example, Buckminster Fuller. Or now it's very typical of additive manufacturing because it allows to print in the space. So that means that you don't have to make molds like the one we saw before. It's a completely different technique that gives you much more freedom. So the idea from this project was to work with different density of the design in relation to where are the bigger loads. Where we have a higher loads, we have different types of porosity. Where we have lower loads, we have lower porosity. So this was mainly the process, so taken from nature, let's say, but in a more innovative way, understanding so which is the current bone structure with other strains, and then trying to remodel the structure in order to have the right mixture of cladding and of load-responsive cellular solid. We made different experimentation, understanding how much we could work with permeability, density, and printability. So here too, I think the main issue and the opportunity was to embed in the design the different issues from the very beginning. How much density can I give to the structure? What are the loads I can take? What type of material and which is the type of characteristic this material have? And how can I print it to? Trying to improve at the best also the printability. Then we tried to make some experimental component with different density, and this was another exercise to understand how it could work in permeability, lightweight, and different type of structure. This is part of the structure with the material distribution. We made some tests to understand this type of structure because it's quite experimental, but I think this mass customization in construction is experimental because it tries to push us a little bit the border between a very traditional way of designing with standard construction system and trying to customize our own construction system. And we made some different types of compression on this lattice structure. A small brick of 360 grams can take a load of 300 kilos, and 300 grams was 1 ton. So it was quite a good result for a structure that is made with polymers, so mainly thermoplastic polymers, that usually doesn't have such a big resistance, but they can work very well because also of the design. We made already some samples in different types of exposition, let's say, and this is where you will see it in a while. I think the base is there, and you will see the structure in a couple of weeks. So this too was made with a research project of PhD, but also with some students, with intern, thesis. So it was quite a good exercise for students to understand which are the opportunity to push in the design, which are the competencies you can rise with this type of technologies. Then in construction, of course, there's a lot of accent on very traditional materials like concrete, for example. And in concrete, we have worked with columns to face the possibility to have a concrete that could work also structurally and that can have like a torsion in this case, so to allow a shape that could be very difficult in precast technologies. I think it's very important to think that additive manufacturing is not substituting the construction sector in some material, but it's more an hybrid technology. So where some things could be very difficult or expensive in the manufacturing way we are making now, we can add with these new types of technologies. And another vice versa technique that is quite useful is molding. So it's different types of molding with 3D printers. The idea that you can make different types of casting, so to allow particular shapes, to allow to have holes. I have this example here. To have twisted shapes, to have different types of aggregates. I think this is a very promising sector too. It's important to try to push the boundaries, which can be the experimental possibility, also to try with traditional materials, traditional techniques like molding, but trying to push it with this computational design and with the new possibilities of the machine. Then I have this example that is also quite nice on this mass customization on construction system. It's printing with sand and wind. It's a project we are following with the overlay division of Expo 2020. And the concept was, let's make a shading. In this case, it's an external shading, and it has to remind the desert, but also to remind a very transparent structure. This is the Jean Nouvel Louvre in Abu Dhabi. So it's a completely permeable structure that let light inside to have a very particular experience of the museum. So this is the building. It's a study on this concertina pavilion. Concertina pavilion are the pavilions that are not part of the country pavilion. It's like mainly services pavilion, meeting rooms, prayer rooms. And the idea was, let's try to have a cladding, an external shading that can remind the idea of the desert that we can see in all the different concertina pavilion, because there are a lot, but that can also remind something when you see all of them. So it's customized, but reminding with the same design. So it's a real sort of mass customization. It's more open where we have lighting on the back, so the idea is that you can see inside, and it's more closed where you don't need to have transparency. We made different studies trying to understand how this shape could work in relation to the idea of the design, so of the type of sand we were working with. We make different types of small models. I think this is also what we are trying to do here. So it's first of design phase, then embedding the materials, and then trying physically to understand which will be the result. We made different trials with different types of materials. One is PLA plus paper. It's a sort of HT-PLA, so it's high temperature PLA, because this type of material, it's a biopolymer, but that has a melting temperature around 90 degrees. So for UAE climate, it was a little bit tricky, because even here we are a warm climate, but UAE is even worse. Then we tried with cement and Dubai sand to work maybe on a more durable solution. And then we worked with resin and Dubai sand. That was more or less the final idea. This is the structure, so it's a secondary structure within different types of component. The challenge and the opportunity of additive manufacturing is that you can decide how you want to cut the different types of components. You don't need to have, we had a modularity that is done mainly by the machine, but then on the horizontal line we could do whatever we wish for, and this was quite useful also to make the right component. These are some other examples of the whole assembly of the facade. And this is, it reminds the design we were doing at the beginning. So trying to work with this wind and sand to make the different components, and then to try to go to the prototyping. We work with then an abacus of facade system to understand how it could work, and an optimization of the different components. This is one of the printers we have used in this prototyping. We have it here in Politecnico, so I don't know if some of you will go for a full-scale prototype in the project. Maybe could be an idea. It's a very big one. It's called 3 meter, but the printing area is 1 meter by 1 meter by 1 to 20, more or less. And this allows to be quite fast, because one of the issues of additive manufacturing is that it's very slow, so it takes a lot of time to make the component. I think we are quite ready manufacturing in additive to make components components that could go on site, there's a sort of problem on legislation. Because here too, when we start to understanding, we made a full mock-up of the prototype, and then we say, okay, but then if someone is installing this, who is taking the responsibility for an object that is 3D printed, is not an industrialized, manufactured component? And I think this is a very big issue that will come in the next year. So which is exactly the context that can allow these innovative technologies to go through in the market? So who can guarantee what are the type of tests? This was the different parameter we were working with. So the different extrusion, the time, the temperature, and this, for example, this printer is working with pellets, so it's not working with filament. So usually when you work in different small sectors like design, you work with filament. Well, in this specific sector for construction is a little bit different because we work with pellets, so it's small balls of plastic. And this is very useful because it allows to make the mixture you like to make. It's a little bit as we saw at the beginning. So you can like customize the material you're working with and you're designing. And then it allows to be faster. That is for construction, one of the biggest issues. And this is the extruder. As you can see, it's much more bigger. And there's a lot of research on manufacturing techniques. So which type of manufacturing could work for construction, also on CNC machine, on hybrid system of manufacturing, on robotics, of course. That is more complicated for construction, but can be very useful because you have more axes. In these cases, you have only 3. And sometimes you can have 4 if the plane is moving, but mainly it's 3 axes, while when you use robotic, you can have more axes. Even if construction, as I said at the beginning, it's a little tricky sector, because innovation is less needed than in other sectors. In other sectors, you really have to push, because you have to change the product, you have to update in relation to competitors. In construction, it's a very stable sector. It's capital goods, so it's something that stays for a very long time. So innovation happens more in an experimental way in some parts of it. So it could be a construction system. There's now a lot of research on augmented workers. So how the workers can better deal with the site. So instead of being traditionally assembled, this component could be seen with iPads or augmented reality. So you can really work in an environment where you know what you're doing. And then I think this, to close it, it's mainly this idea of the future of mass customization. Is that it's an evolution that would materialize the idea of an almost complete customization, where you can really know exactly how your building is working. A little bit like sailing or other type of sectors where you know exactly how your boat is made. I think construction is going in this direction. So where you know exactly what types of components, which are the loads, which are the materials, because you have designed them, you have tested them, and you better know what is your final construction products. So this is the wish, let's say. Okay, thank you.